Greetings, chemistry students. Today we're going to talk about polarity of bonds and molecules. So to start, sometimes there's an uneven sharing of electrons between atoms, which makes what's called a polar bond. So this is in covalent compounds where they are sharing their electrons. Well, because they have different electronegativities based on which atom you're working with. If you remember from a few weeks ago, fluorine is the most electronegative element. Francium and cesium are the least electronegative. Well, if there's a difference in electronegativities, the more electronegative atom will pull the electrons that are being shared closer to itself in the molecule. So for instance, if we look at the hydrogen fluoride molecule, fluorine being the most electronegative element will pull the electron pair that's being shared, that's this pair right there, it'll pull it closer to itself, making the fluorine side of the molecule a little bit negative and the hydrogen side a little bit positive. So that's what we're talking about with polarity of bonds. Now, in a molecule, if there are polar bonds, so there's bonds that have differences in electronegativities, and they're arranged asymmetrically, they're not symmetrical around the molecule, which is typically caused by having lone pairs on the central atom, the molecule itself is polar. So for instance, if a molecule is bent or trigonal pyramidal, the molecule itself will be polar. Now, there are other cases where molecules can be polar. We're not going to go too much into that in this class. But essentially, an uneven distribution of charge within a molecule leads it to become polar. And this has huge significance for the molecules themselves because there's this principle, like dissolves like, meaning polar things dissolve other polar things. So if we take a look at this shows us a hydrogen molecule where they evenly share their electrons. If we look at a water molecule, oxygen being more electronegative pulls the electrons more towards itself, making the oxygen end of a water molecule negatively charged and the hydrogen end of the water molecule positively charged. And that has some pretty huge significance, as you will see in this little video clip right here. For this demonstration, I have a balloon and I have a stream of water flowing from this faucet. I'm going to rub this balloon against my hair to charge it up with some static electricity. And then as I hold this balloon near the water, you can see that the water is deflected by the balloon. So the water molecules are attracted to this balloon that has a static charge on it. And that comes down to the polar nature of water. So as you saw, the fact that this water molecule has an uneven distribution of charge means that it's attracted to that statically charged balloon because that balloon has a negative charge on it, and so the positive end of the water molecules is attracted towards that balloon, and it pulls the entire stream of water towards it. Other example of a polar molecule, we have hydrogen fluoride, where fluorine's more electronegative than hydrogen. We also have nitrogen trihydride, also known as ammonia, NH3. It's a trigonal pyramidal shape because it's got that lone pair of electrons up top. Nitrogen's more electronegative. It pulls the electrons towards the top of this molecule. So this molecule is also polar. Now, an example of a molecule with polar bonds that's nonpolar is carbon dioxide, because oxygen is more electronegative than carbon, so it pulls the electrons towards each side. But the thing is, this molecule ends up with it being negative on each side and positive in the middle, which is not like a magnet. Magnets have a north pole and a south pole. Polar molecules have a positive end and a negative end. Well, this molecule has two negative ends with a positive middle. That's kind of like an Oreo cookie. This molecule is not polar. Carbon dioxide, nonpolar. And it's a nice linear molecule. So there are some significant things at play with this, because depending on whether a molecule is polar or nonpolar will have some pretty significant impacts on what happens when you put these molecules together. So like molecules will dissolve other like molecules. Unlike molecules will dissolve unlike molecules, as I'll show you in this little demonstration. In this jar is a mixture of oil and water. Notice the oil is on top of the water because oil is less dense than water. And the water, I've added some red food coloring to help you see the difference. Now if I shake it up, what you might notice is that the oil droplets and the water droplets, the oil literally gets squeezed out of the water. As the water molecules come together and form those hydrogen bond interactions with each other, it literally squeezes out the oil, which is why you end up with those little bubbles of oil. There's water droplets trying to squeeze it out, and that's why ultimately it ends up separating back out. Is the water molecules are more attracted to themselves than they are to the oil. So as you saw there, the water molecules like to stick together because they're polar. They're like a bunch of magnets, so they stick to each other, and the oil, which is nonpolar, is not attracted to the water. So the water kind of ignores the oil, and because the water sticks to itself, the oil gets squeezed out, and since it's less dense, it just floats to the top.